Now, by minimizing RSS of beta, we can obtain estimates beta 0 hat, beta 1 hat through beta p hat of the parameters beta 0 through beta p. Okay, this method is called the least squares method. Let X be this matrix. So here we have a bunch of 1s along the first column, then x11, x21 through xn1 in the second column, and so on. And we let Y be the column vector of y1 through yn. Okay, then y minus x beta is going to be equal to this minus x times the column vector of betas. Okay. And that's equal to this minus this matrix. Okay, we just multiply this matrix by this column vector. Okay, we simplify here. Okay. This is just f of x1 and so on. F of x2, f of xn. Combining, we get y1 minus f of x1 through yn minus f of xn. Okay, so y minus x beta transpose times y minus x beta, that's going to be the sum of the squares of yi minus f of xi. Okay, so we found y minus x beta here, that's equal to this. Okay, so when we take the transpose and multiply by itself, we get all these entries squared and we sum them up. So that's what we have here. Okay, and that's just equal to the RSS of beta. Okay, therefore the RSS of beta is y minus x beta transpose times y minus x beta. Consider the vector of partial derivatives of RSS of beta. So consider this, the derivative of RSS of beta with respect to beta 0, with respect to beta 1, and so on. Okay, now the RSS of beta is y1 minus this squared plus dot 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 plus yn minus this squared. Okay. Now let's take the derivative of that with respect to beta. Okay, so here we have a power of 2, so we drop that, multiply by the derivative of the stuff inside. Here we have the derivative is -1 since we're taking with respect to beta 0, so we multiply by -1 here. Okay, we go all the way down the line and we get this. Now that is just equal to -2 times this row vector of 1s times y minus x beta. Okay, let's take the derivative with respect to beta 1. Okay, so that's, once again, we dropped a 2. We have the stuff inside times the derivative of the stuff inside with respect to beta 1. Here we get minus x11. Go all the way down the line, we get minus x and 1 here. But that is just equal to negative 2 times this row vector, x11 through xn1, times y minus x beta. Okay, so we see a pattern here. In general, the partial derivative of RSS of beta with respect to beta k is negative 2 times the row vector, x1k through xnk, times y minus x beta. Okay, so this column vector of the partial derivatives is equal to this. Okay, we just found this here. And that's equal to minus 2 times this matrix times y minus x beta. Okay. And that right here is just x transpose. So the whole thing is equal to minus 2 x transpose y minus x beta. If we take the second derivative of RSS of beta, say the derivative of RSS of beta, first with respect to beta k, then with respect to beta j, we get the partial derivative with respect to beta j of this here. Okay, and that's equal to 2 times x1j x1k plus dot 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 plus 2 xnj xnk. Okay, so factoring the 2 out, we get this. Now note that x equals to this matrix. Okay, so therefore x transpose x is equal to this. Which is equal to the matrix where the jkth entry is ajk, where ajk is this. Okay, so the second derivative of RSS of beta with respect to beta k, beta j, that's equal to 2a sub jk. Okay, so the matrix of second derivatives of RSS of beta is 2x transpose x. Okay, and this matrix is called the Hessian. It's the matrix of second derivatives. Okay, now by the second derivative test, if the Hessian of RSS of beta at a critical point is positive definite, then RSS of beta has a local minimum there. Okay. Now, if we set our vector of derivatives to 0, we get negative 2x transpose y minus x beta equals 0. Okay, multiplying this out, we get this. And so 2x transpose x beta is equal to 2x transpose y. Divide out the 2, and we get this. Now, here we're trying to isolate beta, so take the inverse of x transpose x. Okay, we get beta equals x transpose x, the inverse of that, times x transpose y. Thus, we solved for the vector of parameters, beta 0 through beta p, which minimizes the residual sum of squares RSS of beta. So we let the approximate values beta 0 through beta p be given by x transpose x inverse x transpose y.